All right, guys, big lesson, special segments of triangles. We got a lot of information to get through, and I'm just going to go right through. So special segments of triangles, the first one we're going to talk about is called a median. And you have to know two critical things for all the special segments. The critical things that medians have to do is they have to connect a vertex to a midpoint. So it has to hit a vertex, and it has to hit the midpoint of the opposite side. That's what it must do. So I'm going to go create one of those real quick. So what am I talking about? If I got myself a triangle, I need to find the midpoint. Boop. And I have to draw a segment that connects the vertex to the midpoint of the opposite side. What I have here is a median. I know that those are two equal I know that these are two equal distances. It hits the midpoint of the opposite side. Boom, nailed it, median, got it down. So median, we think of the word middle, it has to hit the middle of the opposite side. If you were to draw it out for yourself here, an example of a median, you have to start at the vertex and you have to hit the middle of the opposite side. So it might look something like that. When you draw all three medians, so if I go in here and I find all three midpoints, so E is a midpoint, F's a midpoint. If I connect those with segments, they hit at a spot. You see how they all hit in one spot? They all hit point G there. And it doesn't matter what I do to the triangle. It doesn't matter what kind of triangle it is. The medians will always intersect at a single location. So that spot has a name, and it's called a centroid. So it's called a point of concurrency. So hold up, let's rephrase. The general category is point of concurrency. And I'm going to call this POC because I don't want to write all that every time. For medians, the POC is called a centroid. I know that's kind of confusing, but it's like if I had a general category like mammals, what is a specific type of mammal? It'd be like a lion or a bear or a dog. Those are specific mammals. Well, the centroid is a specific point of concurrency that happens when you have three medians intersecting. So this spot where they all hit is called the centroid. It is a type of point of concurrency called a centroid. It'll make more sense when we talk about some other ones in a second. But the centroid has two special properties, and you have to know them both. It is the center of gravity. Now, we're not going to do anything with that other than you just need to know that property. So a test question might say, which point of concurrency is the center of gravity? Well, that answer would be centroid. The other thing it does is it splits the median 1/3, 2/3. So it splits the median 1/3, 2/3. This one we will use to solve some problems. What do I mean by that? Well, if I call this A, B, and C, I am saying that 1/3 of AC would have to equal BC. And 2/3 of AC would have to equal AB. So if AC equals 27, right? If the whole thing from A to C is 27, then I know that BC is 9, 1/3 of 27 is 9, and AB is 18. 2/3 of 27 is 18. So we're going to use this property to solve a few problems. And it doesn't matter which piece you know. For instance, if I knew that this was 10, AB was 10, well, I know that 1/3 is half of 2/3. So if that's 2/3, then 1/3, has to be 5. And then you would know AC is 15. So if I give you any piece of a median, you should always be able to find the other pieces by understanding this property, that it's split into 1/3 and 2/3. So here's the things you have to know about a median, and you have to know them quickly. It connects a vertex to the midpoint of the opposite side. Three medians intersect at a point called the centroid. The centroid's the center of gravity, and it splits the median 1/3, 2/3. Those are the things that you have to know about a median. Next situation that we're going to talk about is called an angle bisector, and we've done this one pretty much the whole year. I don't remember when exactly, but early in the year we first introduced angle bisectors. Angle bisectors, they cuts the vertex in half. So it's kind of a stretch, but it does two things. It must hit the vertex. That's the first thing. It must cut that vertex in half. That's the second thing. So if I were to draw a triangle here, an angle bisector would cut the vertex in half. Boom. And I can draw all three angle bisectors. They must cut the vertex in half each time. And then once again, just like medians, they do hit at a spot. And for this one, the POC is called the end center. So there's different POCs, just like there's different mammals, right? Lions and tigers are different mammals. End center and centroid are different points of concurrency. The centroid is where the medians hit. The end center is where the angle bisectors hit, and they are different spots. So if I go over here, if I were to create an angle bisector, actually, let me just make a new situation. So let's do angle bisectors. So we're going to make a triangle. We're going to create some angle bisectors here. So I'm going to cut that vertex in half. Boom. I'm going to cut vertex A in half. Boom. I'm going to cut vertex C in half. Oh, dear. I messed up. Undo. And the spot where they hit, that's the end center. That is not the centroid. It's a different spot. Now, I can move the triangle around. It never leaves the triangle, but it is not where the centroid is. Want me to prove it? Let's find the midpoints. The midpoint of this side. Does the angle bisector go through the midpoint? If I connect C to F, that's the median. Sorry, that's an E. CE is a median. That is not an angle bisector. Medians and angle bisectors they're not the same line. Are you looking at it carefully? They're not the same. So where's the centroid? Well, if I were to find all three of them real quick, the centroid is over here. So the centroid is not at the same place as the end center. Are we seeing it? I hope we're seeing it. Okay, let's focus on the angle bisector real quick and the single median. So check this out. Now I said they're not the same thing, right? You heard me. I said it and you heard me because you listen when I talk. Now what about, let's take a look here. What if I'd already kind of spoiled it. Check this out. Right now, the angle bisector and the median are different lines, right? Black and blue are different. Do you think I can make them the same line? Well, that's not helping any. How about over here? Look at this. Do-do-do-do, do-do-do, do-do-do-do, whoop! Oh, it's a little bit off. I can do better than that. Maybe something like that. Oh, that's about as good as I can get it. I'm not too worried. But yes, they can be the same line. What is going on here? What is going on here? What do you see? Those are really close, aren't they? It's almost isosceles. When it's isosceles, the median and the angle bisector are the same line from the vertex angle. Now, if I zoom in, they're still actually different. Why is it not perfect? Well, it's because I didn't make a perfect isosceles triangle. If it was perfectly isosceles, they would be the same line. All right, we're going to talk about we're going to talk about that more here in a minute. The end center has a special property. It is equidistant. What does that mean? Equidistant? That means equal distance from all three sides. It is equal distance from all three sides. That's one of the things that I'm not going to go into detail. It's its own lesson. It's not a lesson we're going to be able to do this year. As we've talked about a few times, we have a lot less time on a block schedule, and that takes a full class period, and we just don't have that class period. So we won't be doing anything with it, We just have to know. So if I say which point of concurrency is equidistant from all three sides, you need to know that that's the incenter. That's what you need to know. Angles are in, bro. Angles are in. Angle bisector, incenter. All right, the next one we're going to look at is called a perpendicular bisector. And the names kind of tell you what they do, right? Median hits the midpoint. Angle bisector bisects or cuts the angle in half. Perpendicular bisector, it's going to hit, that's not the word hit, it's going to hit the midpoint at a right angle. Two things, hits the midpoint of the side at a right angle. Did I mention anything about hitting a vertex? No. So angle bisector has to go through a vertex, has to cut the angle in half. Median also has to go through a vertex, but it has to hit the midpoint of the opposite side. Those are the two things a median must do. But like we said a second ago, could a median also cut the vertex in half? It could. If it's isosceles, it does that from the vertex angle. Well, a perpendicular bisector must hit the midpoint at a right angle. So if I'm drawing a perpendicular bisector, I'm finding the midpoint, and what I'm doing is I'm hitting it at a right angle. That's a perpendicular bisector. Does it have to go through the vertex? No. Do you think it can go through the vertex? And the answer is yes. I'm going to draw these perpendicular bisectors real quick. It's going to look something like this. And again, oh, this is not drawn very well. That's okay. I'll show you in GeoGebra. This is definitely messed up. That does not look like the midpoint, but that's okay. So perpendicular bisectors, they hit at a point, and it's because it looks really, this is actually really close to a right angle, so I definitely have it off a little bit. But its POC is called the circumcenter. And its special property is that it is equidistant, there's that word again, equal distance, from all three vertices. All right, so that's everything we need to know about a perpendicular bisector. Well, not everything, but a lot of things. So let's go in here. I'm going to make some perpendicular bisectors. So we got our triangle. We're going to go in here. We're going to do somewhere perpendicular bisector of each side. So there's my perpendicular bisectors. All right. That spot where they hit is called the circumcenter. What does circum mean? Circum means circular. We're going to talk about that here in a second. But look at that circumcenter. Look at it. Where is it? Right now it is inside the triangle. If I were to measure this angle, it's 87 degrees and it's inside. Watch it. Watch point D. Watch point D. Are you watching? It's in, on. It's on. What kind of angle do we have? It's a right angle. Now, it's not perfect. If I zoom in, is it going to be a little bit off? It sure is. It's a little bit off. Now, I can't tell from here. I can't tell from here that it's a little bit off, but I could when I zoomed in. If I go, can I make it better? Can I make it better? I can't make it better. I can't do it. Can I do it? Oh! Right at 90. And now, see, it's even still a little bit off. The reason why is this program does round. So it might be like if I messed up. But when it said 90 degrees, it might have really been like 90.0022 or something. So if I zoom in big time, yeah, you can still tell. But now we're out. What kind of angle is that? Obtuse. Out, on. In, on. Now which angle is the right angle? That's right, angle A. Out. Which one's obtuse? A. In, on, out, on, in. So we need to know about the circumcenter, that if it's an acute triangle, it is in the triangle. If it's a right triangle, right on, dude. And if it's an obtuse triangle, it is outside the triangle. You must know that information. And it's going to come back again later. So I am going to do a little copy paste because I want to save that for later. All right. But where's the circum part of circumcenter? Well, I told you guys it's equidistant from all three vertices. Ah, wrong one. Wait, no. Wait a second. There we go. It's equidistant from all three vertices. What does that mean? Well, that means if I find the distance from D to A, if I find the distance, oopsies, from D to B, if I find the distance from D to C, they're the same number. Those, doesn't matter what I do, they're going to be equal to each other. So those distances, D to A, all of them, they're the same length. That means if I make a circle and go from the center to the vertices, it's going to be a circle that goes through all three vertices.
Students, want to let you guys know, if you hadn't heard, we will be having our first pep rally of the year.
Check it out. I know you can hear the announcements. I'm sorry. We have a pep rally on Friday. Hopefully it's not overwhelming, but it doesn't matter what I do to this circle. It is going to be isosceles. It is going to be equidistant, and that circle goes through all three vertices. Goes through all three vertices, my friends. All right.
So you need to treat it like a normal C day, follow the same shuttle schedule that you would follow. So if you travel for sixth period, you're going to take the normal shuttle over for sixth period.
The last type's called an altitude.
If you travel for second and sixth as a block, when you guys get back, you're actually going to be in the middle of our sixth period. So you'll need to go straight to lunch, and then you guys are going to report to the library for the rest of sixth period. Then you can go to third period as normally scheduled, and that's when we're going to have our pep rally. If you guys travel for third period, you need to follow the same normal shuttle schedule for third period, which is going to actually be in the middle of our sixth period.
So if I have this situation, I'm going to have to talk with here. An altitude starts at a vertex, and it is perpendicular to the opposite side. That's an altitude. Now, we're used to altitudes meaning heights, meaning vertical. But guys, in geometry, it's how does it relate to the other things that we're going over? Or the other things in the picture. Sorry, the announcements are really messing me up here. But we have, before we talk about isosceles triangles, if these two sides are equal, which side's the base? This is the base, right? It's not the bottom. Like if I say the base of a building, yes, I mean the bottom of the building. But if I say the base of an isosceles triangle, it doesn't have to be the bottom. It's how does it relate to the vertex angle? That's actually what the base is. So in geometry, it's not always where it physically is. It's how does it relate to other things. It's the context of the problem. So the base of an isosceles triangle doesn't have to be the bottom. Altitude doesn't have to be a vertical height. And that's where this gets really confusing. So an altitude, like we think of altitude, we think of planes, right? Like a pilot would be like, we're flying at an altitude of 30,000 feet. Like you're up here in a plane, and, planes soaring through the air at high speeds. I'm a teacher, so I'm way back here, and I'm in this plane. And they say you have an altitude of 30,000 feet. What are they talking about? What is that altitude? Well, the altitude is actually the distance above sea level. So you have the ocean over here. You got some fishies in the ocean. You have some wildlife. Right? A little turtle, a little fish. So, got this stuff in the ocean. Does that mean that you're like 30,000 feet from the ocean? No, you could be like flying in Colorado or something, right? Like, you could be over here in Colorado and the ocean is really far away. So what is the 30,000 feet? It is how far above the ocean you are if the ocean continued to your location. So you don't have to actually be above the ocean to say you're 30,000 feet above sea level. You don't have to be above the actual ocean. So that gets a little tricky. If you actually made a triangle with the ocean here, it would be an obtuse triangle. So we're going to get to that in a second. But altitudes don't have to be vertical lines. Altitudes, they just have to be perpendicular to the opposite side. So like if I go here and I go perpendicular, And then if I go here and I go perpendicular, boop, there are my 3 altitudes. They just have to be perpendicular. And they're going to hit at a POC called the orthocenter. There's nothing special we're going to do with that. You just have to know, if I say which point of concurrency do the 3 altitudes make, it's called the orthocenter. But there's 2 situations you need to be aware of. If I were to draw a right triangle, call it ABC, that has 2 built-in altitudes. AC is an altitude. AC starts at A, and it is perpendicular to the opposite side. What's the other built-in altitude? That's BC. BC starts at B and is perpendicular to AC. Remember, altitude doesn't mean vertical. It means vertex perpendicular to the opposite side. And then the third altitude is actually in the triangle. So on this shape, the orthocenter is the right angle. There's my orthocenter. But it gets a little wonky. Ooh, remember this situation? And we don't like this, and people miss this all the time. If I have an obtuse triangle, oh, that was so close. I can do it. I can do it. I can do it. I can do it. Yes, I can. Ah! Please, please, Notability, please. Nailed it. So you just had to say please. You just got to say please. All right, triangle A, B, C. If I'm going to draw these altitudes, dang, here's vertex A. I got to be perpendicular to BC. Can I be perpendicular inside the triangle? Are any of these perpendicular options? No, it's got to be here. Why here? What? Huh? Mr. Man, what? Why? If you extend this side, just like if you extend the ocean, that's the spot where you would be perpendicular. So it doesn't actually have to touch BC. At nowhere in the definition did I say it hits BC. I said it's perpendicular to BC, but I never said it touches BC. Oh, how about this one from vertex C? Again, I cannot be perpendicular inside the shape. I can't do it. But if I go out here, doop, there we go. There we go. Extend, extend. Yes, yes, yes. Perfect. 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 That's where it would be perpendicular. So I didn't extend it very good, but it would be perpendicular. It's where it would be perpendicular if you extend it. And then the third one would be here. So where do they all meet? Well, if you kept drawing these lines, they're going to all meet somewhere out here. So the orthocenter is going to be way outside the triangle. So remember I copy and pasted earlier? Orthocenter is the same situation. Acute inside the triangle. Right on, dude. And obtuse outside the triangle. On an obtuse triangle, 2 of your altitudes never go inside the triangle. That's a tough one. A lot of people are going to mess that up. All right. So let's go back to this situation. Nope, actually, it's time to go to the main event. So we've talked about what all the words mean. And on your quiz, on your test, all those things, you are going to have to be able to rattle off information quickly. You should be able to do this by the next school period, guys. So here's what you have to know. If I say median, you need to know that it's vertex to midpoint. It meets at the centroid. The centroid is the center of gravity, and it cuts the median 1/3, 2/3. I say angle bisector. You need to know that it cuts the vertex in half, that they meet at the end center, and that it's equidistant from all 3 sides. I say perpendicular bisector. You need to know that it hits the midpoint at a right angle, that it meets at the circumcenter, and that it's equidistant from all 3 vertices. I say altitude. You need to know that it starts at a vertex, it's perpendicular to the opposite side, and that they meet at an orthocenter. You need to be able to rattle that off in about a minute, kind of like what I just did. All right, there is some more stuff we're going to talk about. So let's talk about in-center versus circumcenter. Here's the types of problems I could give you on a test. Let's say that I am starting a snow cone shop, right? So I have my snow cones. And I want to make it equidistant from 3 highways that make a triangle. Well, it doesn't have to be highways, but like anything that could represent lines. So 3 highways that make a triangle could be 3 sidewalks, 3 hallways, 3, pencils, 3 toothpicks. If it represents a line, how are you equidistant from 3 lines? That would be the in-center. So I would want to put my snow cone shop at the in-center. That's the type of test question I would ask. I want to build a snow cone shop that's equidistant from 3 highways that form a triangle. Where should I put it? At the in-center of the 3 highways. What if I changed it up? What if I wanted it to be equidistant from 3 middle schools, like CMS North, CMS East, and CMS West? So you're like, I want to be as close as possible to all 3 schools. Well, those represent points. So if I want to be equidistant from anything that represents points, then I need to be at the circumcenter. So that answer would be circumcenter. So when you're reading these questions, be thinking, would that represent a line? Then I need to be at the in-center. Would those represent points or single locations? Then I need to be at the circumcenter. All right, now let's go to the main event, the moment we've all been waiting for, and I made this ahead of time just for you guys. Hopefully this opens up correctly. I had trouble earlier. There we go. There we go. So I'm going to measure some things so that we can see it. This is a slightly different interface. I'm not used to it as much. I don't know why it switches interface on me. All right, I'm going to take this. I want to grab the number. You going to let me grab the number? Nope, it's not. It doesn't like me. Okay, so maybe the numbers will be hard to see. I can't get the numbers to move. It's just moving everything. All right, it doesn't matter. But we have the 3 side links. They're kind of hard to see. But what we're going to do is play with this a little bit. I drew every possible special segment. Every single one is here. The pink ones are angle bisectors. The black ones are medians. The blue ones are altitudes. And the green ones are perpendicular bisectors. So like that's a circumcenter. The black ones, I said those are medians. That's a centroid. That's an in-center. So we have all the special points. Are they the same point? No, they're different points. But what happens if I make my triangle isosceles? So if I make my triangle isosceles, oh, were we watching? So it's not perfect, but it's pretty close. Angle C is the vertex angle, right? CB and CA are equal. And those lines, it was 4 lines. Now it's 1 line. And they're really close. I know it's 13.32 and 13.33. It's super close. If I zoom in, guys, it's actually still 4 separate lines. And it might be really hard. I only see 3. If I keep going, yeah, there we go. Those 2 are separate. They're 4 separate lines still, guys. You have to zoom way in to see it, but they're 4 separate lines. Why? Because it's not perfectly isosceles. If it was perfectly isosceles, they would be 1 single line. So here's something you have to know. What does that mean for you? That means for you, if I give you an isosceles triangle, right? So let's say that these 2 sides are equal. And then I tell you that this is an angle bisector. If it's isosceles and you know it's one thing, it could have been anything. I chose angle bisector. I could have done median. I could have done altitude. I could have done perpendicular bisector. It doesn't matter. If it's isosceles and you know it's one special segment, then you know it's all special segments. So AB is an angle bisector, but it's also a median. It's also an altitude. It's also a perpendicular bisector, and you have to know all those things. So an isosceles triangle, from the vertex angle, you have all 4 special segments at once. On the flip of that, if you got a triangle here, and let's say that I tell you, what if we draw this, and we'll call this AB. What if you know that it's an angle bisector and you know it's a median? So in the given, it says AB is an angle bisector, AB is a median. If it's 2 things, then it has to be all 4. At no point can you ever be just 2 things. So we now know that it's also an altitude, it's also a perpendicular bisector, it's also isosceles. Because the triangle is isosceles, you even know that these base angles are equal. You know so much more. So if you have 2 special segments at the same time, any two, then you know you have all 4. You cannot be just 2. You cannot be just 3. You are either 1 or you are 4. There's no in between. Now, from the other 2 corners, it would still be 4 separate lines. But from the vertex angle, it is 1 line that represents all 4. 1 line represents all 4. When it's not isosceles, when it's scalene, they're separate. So boom, one line, all four. Okay, well, what if it's an equilateral triangle? Oh, yeah, let's go. We can do it. Oh, that's a little bit more off than I can do better. I don't know. That's about as good as I get. When it's equilateral, they line up from every corner. So vertex A, one line. Vertex B, one line. Vertex C, one line. It's one line from every corner, but it's everything. They're angle bisectors. They're medians. They're perpendicular bisectors. They're altitudes. They are all the things. And what's more is pay attention to the special points. Right now, G, J, H, and I, look at them. They're four separate points. 4 points, 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 4. Can I do it? 1. Oh, I picked up my finger and it moved. 1. That's about as good as I can get. Now, if I zoom in, obviously they're still off a little bit, right? Why is that? That's just because they're not perfectly, it's not done perfectly because I'm not perfect. I can't get it perfect. If I zoom in, it can be a little bit easier maybe, but still can't get it perfect. But they line up. If I made it perfectly equilateral, they would line up perfectly. That means 4 points becomes 1. So the questions could be like, sometimes, always, or never. The end center is the center of gravity. Well, that answer is sometimes, because when it's equilateral, it's true. Now, the centroid is always the center of gravity, right? The centroid is always, but the end center can be. And that's kind of the stuff we're going to be doing going forward. Thank you for watching the video. Sorry about the announcements in between. Hopefully it wasn't too bad. Let's go.